Thank you, John-san, and thank you, Kazuya, and all the organizing members for this great symposium. I was really impressed at the contents of so far. I'm Motoaki Sugiura, and I'm affiliated to two institutes. One is the Institute for Aging, and another is Institute for Disaster. So I'm obviously not an applied linguistics. So yeah, I'm cognitive neuroscientist, and I was kind of disappointed is that I thought I will today I see many applied linguists, but actually most of the people are almost cognitive neuroscientists. So you are so acquainted with these issues. So so this may be too basic, but the cognitive neuroscience for me it is to understand human mind and behavior based on functioning of the brain. So my interest is to understand human. So and it's applicable to many contexts like aging issues in society or disaster education and many other issues related to human mind and behavior. And of course, it contains language learning. So it's my stance. And so facts to think about human mind and behavior as a cognitive neuroscience. The keyword is cognitive processes. For example, we meet friends and say hi or hi, thank you for yesterday. And in this very simple conversation, we can understand their mind and behavior in many ways. But cognitive neuroscientists understand their mind and behavior like this way. So what happened in the mind of this guy or in the brain of this guy when say hi, thank you for yesterday. So he processed the visual information of his face and actually recognize the face and also hear his voice and process this as a voice and recognize the person and also understand the semantic content of his speech and remembers several episodes, yesterday's episode, and bring some emotional response, and he plans some behavior and plans some speech and produce that speech, controlling his many muscles around his face. So here these rectangles, each rectangle corresponds to different cognitive processes. So we will dissociate many cognitive processes included in apparently or sometimes complex behavior or mental phenomenon. And cognitive neuroscience or researchers of functional neuroimaging will visualize these cognitive processes using these neuroimaging techniques and sophisticated or sometimes simple experimental design, and then identify some brain area or network for specific cognitive process. So this is what I do every day. And I'll tell a little bit about neuroimaging techniques. As you've already shown some really excellent examples by Kazuya and Adam, that there's a type of neuroimaging technique that is showing measuring there are two types of neuroimaging techniques. One is measuring the electromagnetic consequence of neural activity. So neural activity has many aspects, but they produce some electromagnetic change around the neuron or neural network, and it can be measured also from the surface of the head. And that includes electroencephalography and magnetoencephalography, and it has very high time resolution. And the excellent example of this using the adaptation of this technique is already shown by Adam. So using such high time resolution, we can measure such FFR. That is the very clever way to use this, the advantage of this technique. The other type of neuroimaging is to measure metabolic consequence of neural activity. It includes, for example, classical positron emission tomography and functional magnetic resonance imaging, or fMRI, that I will talk today. Or recently, the functional near-infrared spectroscopy, FNIRS, become also popular. And this type of techniques are good at localization, and their advantage is the reliability of the localization. And I will explain this fMRI today because I am specialized in fMRI. And MRI obtains volume image of the magnetic characteristics of the body. And in fMRI, we will measure the hemodynamic response of the primarily brain, in the brain. And to measure this in a unit of seconds. So we can measure the dynamic change of this phenomenon in one's neural system. And how this is produced? It's of course produced from neural activity. When neural activity occurs in some part of the brain, it requires energy for that activity. So our brain system will increase the blood inflow to that region, and it causes a washout of the deoxyhemoglobin around there. So, and this deoxyhemoglobin, it's a hemoglobin that is not carrying oxygen. It left the oxygen in that tissue, and this deoxyhemoglobin has specific characteristics, that is to suppress MRI signal in that area. So by washing out this deoxyhemoglobin, we will measure the apparent increase of MRI signal. This is the mechanism of fMRI. Why we can measure neural activity using this technique. So the spatial resolution is not that high, although reliable, but it's not very high. It's like kind of 1 centimeter. Some people say it can measure 1 millimeter, but I would doubt it because the signal comes from the capillary, not the neuron itself. And its time resolution is something like 10 seconds. And when neural activity occurs here, the signal goes up and goes down, and it's like this mountain is like 10 seconds. So fMRI research is quite simple. Data acquisition is so easy. To put subject in scanner, run cognitive task and scan, and take a subject. That's it. Data analysis includes pre-processing, several processes using some PC, and we estimate neural response in each subject and do some statistical test across subjects. However, this is not, of course, it's not all the processes of the research. We need to design experiments. So this part is the most difficult and important aspect. And to design good experiment, we need to know details about this analysis. Otherwise, we cannot really design good experiments that produce good results. So I'd like to explain this part in a little bit in detail. So, yeah, experimental design includes many aspects, like other cognitive tasks in non-neuroimaging domain, like stimulus, task instruction, and conditions. And here, or there can be intervention, and of course we need some control groups, or we need some behavioral parameters for each trial or stimulus, or parameter related attributed to some individual personality. Something unique about the fMRI regarding the experimental design is the sequence of the trials. Sometimes we put trials quite sparsely in timeline. We call it the event-related design because we can see the neural response related to each event. Or sometimes we put many trials in a very densely in a short time period, like 20 seconds, 30 seconds. Both are advantage and disadvantage. It has a flexibility in the analysis, and the advantage of this is high statistical sensitivity due to this dense task loading. But I think this part is specific to fMRI. Other aspects are the same as many other psychological domains. And using this task or using data obtained from the subject doing such cognitive tasks, we will then estimate the neural response in each subject. That analysis for that estimation, we model the condition-specific hemodynamic response. For example, I lost the color here, but here the red trials and here the red model for red conditions. Here it should be blue, and this is a model for blue condition. And we run multiple regression analysis in each voxel of the data. Voxel is the smallest unit of the image, like pixel. And in each voxel, we run multiple regression analysis using these models, and we can estimate the height of this response. So this height is what we call activation in our analysis. And then we obtain the image of the data for each condition. Now we will make subtraction analysis, typically make subtraction analysis. For example, my central research issue is self-recognition, and I started from self-recognition in this field when I was a graduate student. And I presented subject to his own face picture and the picture of his friend, and I subtracted activation. So here what I do is this subtraction. We can assume that in this task there is many cognitive processing, like visual process, face processing, and self-processing, and decision, familiarity decision of this face. So here, activation here includes all these processes. So we can tell nothing from this data pass. But if we subtract this activation from this, and because we can assume this activation reflects the cognitive process of visual process, face processing, and decision-making processes, we can assume that by subtracting these two conditions, we obtain only the activation reflecting only self-specific processes. So how this? So this is an example of how this subtraction works. So when you design design the fMRI experiment, you have to think about these cognitive processes and to design a good control task that can remove all the processes that you are not interested in. And there's also different approach for this task design, that is parametric approach or parametric modulation. So here we need some trial-specific parameters like performance in each trial or rating of something in each trial. Yeah, for example, here this is a face like this. And for example, in this experiment, for example, we can ask subject to rate the attractiveness of each face or familiarity of each face, and there is a parameter for each face. So in this case, we can design this kind of hemodynamic response. This height is correlated with this rating. So using this model as a regressor, we can identify the cortical areas that activation is correlated with this rating. So this is another approach in within subject analysis. So we can obtain this kind of estimate of the activation in each subject using subtraction or parametric approach. Then we bring this image into the second level analysis, that is statistical test across subjects. The most simple approach is to look for common activation across subjects. Typically we use one sample t-test. Here we have many images from all the subjects and identify statistically significant activation in terms of common across subjects. Or we can do this type of approach for difference between pre and post something. Pre-post, we can make pre-post comparison and perform paired t-test to identify common change across subjects. Other approach is statistics. We typically use group comparison. For example, these are native speakers and the L2 speakers. We can see the systematic difference of activation between two groups, typically using two sample t-tests, or one-way ANOVA or two-way ANOVA if we perform pre and post test. So we can basically compare between groups. And we also, if you are interested in individual difference, we can apply regression analysis. You can put any individual specific parameters like performance or personality. You can identify the cortical activation that is correlated with that parameter. So basically we have three types of statistical approach across subjects design. So basically using these various estimation techniques and various statistical test designs, you can create many different ways to approach brain activation during or related to second language learning. Yeah, however, it's a lot of fun to design many creative designs, but it's not that easy for the people who start those fMRI. So yeah, I'd like to give you some 3 example designs that may be quite useful for in this field. So the first one is designed to identify performance-related activation. And so here, if you can use this if you are interested in cognitive processes underlying good performance of something. And we use individual difference analysis. Second example is to see the intervention effect in terms of results. It means that this is applicable when you are interested in cognitive process reflecting the improved performance. You put some intervention and the student get better in some performance, and you will see what happened in his brain. And third approach that I will introduce here is to see the intervention effect in terms of reason. That is, if you are interested in the cognitive process explaining the higher effect of intervention. And here, it's quite similar to this intervention design, but here we will be interested in the functioning of the brain during the intervention rather than after intervention. Here we will be interested in individual difference here. I will explain each example. Yeah, first example, that is performance-related activation. We will make some cognitive hypothesis like some cognitive process may explain the good performance. So in that case, we will ask the subject to perform some cognitive task in MRI scanner. Most of the researchers think of some test of language. And it's okay, of course you can use it, but I would not recommend it at first. I would rather recommend apparently unrelated task, but related to this cognitive process. It's because we will use performance here in the analysis. In this test, because it's performance related, subject performance is different in the scanner. So in a very simple example, subject may press less number of buttons if the performance was bad. So sometimes we cannot dissociate the core cognitive process that is the reason of the bad performance and the expression of that performance, like motor response. So to avoid such contamination, I would recommend to think about something apparently different from this test, and the performance of the task do not correlate with the performance that you are interested in. And related it, and the performance that you will use in the analysis can be, of course, measured in the scanner in this task. However, this performance is, of course, correlated with like motor response or something. So it's also sometimes difficult to dissociate this effect. So I will recommend to use the performance that is measured outside the scanner. Of course, this is the advantage of the inside scanner measurement, because it's tightly correlated with something happened in the brain, actually. measured. So that's a kind of trade-off. But we have to be very careful that the neural activation associated with performance is actually related to some superficial effect of the performance. And example of this analysis is I brought the example from Johnson's experiment, recent paper. Here, Johnson asked the subject to speak, to make communications, speak to this person in the movie, like how do you play like that in the scanner? So subjects are required to virtual communicative speech production in the MRI scanner. So it's easy to assume that some linguistic process may explain the proficiency of the subject. And in this paper, Johnson was addressed the emotional process related to the anxiety. And actually, in her paper, this emotional process is argued in the abstract. It's shown but not addressed in the abstract. Why? Here, the performance, anxiety is not actually performance here, but individual difference parameter. Proficiency is highly related to performance. Of course, highly proficient people can easily make this communicative speech. And actually, the activation was observed in this language-related area that we can easily expect. However, is it interesting? Of course, it may be interesting, but it's quite so reasonable, too much reasonable, because they are fluent, so they can think a lot about linguistic. They can use more linguistic process. So it's highly reasonable, but not that interesting. So that is why it's not included in the abstract. On the other hand, emotion and anxiety. Anxiety do not directly relate to the performance of their performance. It occurs just inside their brain. So it's quite interesting. We cannot really predict what happens in the brain in association with this anxiety. But probably it's likely to be happen in the brain network related emotional process. And actually it happened in the infra, that is related emotion. So we can get mostly expected results in this experiment. However, the take-home message from this design is if the performance is likely related to the very task performance itself, the story cannot be very interesting. So that dissociation is very important in this type of approach. Second approach is intervention effect in terms of results. That is pre-post comparison. In this case also you can assume that for example some process may explain the improved performance, and then you can design some intervention, some learning experiment, and measure the activation before and after this intervention. And here again, it's quite similar to the previous case. That the task you choose in this experiment the choice of the task is quite important. If you choose the test that is too much related to the performance itself, it will produce some uninteresting results like a motor cortex or something. Probably you can choose more apparently different and associated tasks, but specifically addressing this process of your interest. So you can, by showing the change of the brain activation between pre and post by intervention, you can prove that the brain of the brain functioning of the learner actually changes as you expected. And example of this type of approach is, this is unpublished data of a colleague. So this is not a actually not at all language learning task. In this task, my colleague was interested in the debate practice, and here the debate practice is expected to improve the openness to others' opinion, and his assumption is, his hypothesis is that some inhibition process may explain that openness, and which is improved by debate practice. So the intervention method was a part of debate practice, that is, argue the opposite opinion in front of other people. And the cognitive task before and after this intervention was to judge on some basis of others' opinion, like here smoking is a risk factor with several kinds of cancers, and subjects have to decide whether this reason is the basis of the people who argue against smoking or for smoking. And they prepare many kind of those arguments and issues and many bases, and ask the judge whether this is a pro or con basis. And activation during this task is expected to change by debate practice intervention, and they expected that some processes related to inhibition will increase after this intervention. And actually it happened. This was quite small cluster, but this prefrontal and parietal activation is often reported in the process related to inhibition. So in this way, putting pre and post measurement before and after the intervention, we can see the effect or result of intervention in terms of brain activity. Here, what we can learn is that the task performance is quite simple, whether it's pro or con. So we can eliminate the effect of the performance inside the brain from the superficial behavior of the subject. So we can focus on the cognitive process, deeply related the key process of one's interest. And finally, the third type. This approach is not that popular so far, but I personally recommend you to use this. I love this approach recently. So this is also related to intervention, but to see the reason of the effect. And here, for example, yes, you may assume that some process may be key to the intervention effect. And in this paradigm, we will measure the activation during the intervention inside the scanner. by knowing the process of the during the intervention and see the effect of the see the brain activation related change of the performance, we can know how the brain response activity differ between who learned a lot and who didn't learn. So that is by knowing this this neural functioning that explaining the intervention effect, it can be used to improve the intervention method itself. So here, the most challenging issue is to create a cognitive task in this case. We have to create the fMRI intervention task. And we assume that it involves some key processes for learning. And ideally, we can include a control intervention that is similar to this intervention task, but without specific cognitive process. And then we measure the performance between pre and post, and we use this pre-post performance change in the regression analysis in the second level. The example of this approach is, this is also not from the language learning, but my colleague was interested in the effect of reminiscence therapy. It is quite famous in the aging science. Not only aging elderly, but in other young people who have some depressed mood, can improve their mood by remembering many nostalgic events. Feeling nostalgia will improve one's mood. And it's quite famous in this field of mental health. But why it's not, no one knows why this has such good effect, psychological effect. So our assumption was some social cognitive process may be key to the optimism effect. Here, feeling nostalgia will make some people optimistic. So we consider there are several backgrounds, but we assume that there should be some social cognitive process that enhance this optimism effect of this reminiscent therapy. And here we can create an in-MRI reminiscence therapy because we can just present the nostalgic pictures. And of course, there can be some nostalgic and non-nostalgic pictures, but in some, there is half of the pictures are, at least half of the pictures are nostalgic pictures. And before and after this in MRI intervention, we measure optimism score of each subject. And here it's not actually performance, but here the individual parameter is the pre-post change in optimism. And we performed the correlation analysis between this change of optimism and activation during this intervention. And we identified that the correlation was identified this dorsomedial prefrontal cortex. So this is a correlation with optimism increase. This result is a correlation with nostalgia of the picture. So what is interesting is that nostalgia causes activation of many different parts of the brain, but only one part of that activation was correlated with the optimism change. So this kind of approach seems to be useful for many different types of intervention to identify which component of the intervention is really meaningful for the improvement of something. So yeah, basically that's it. So there are three tips that I feel important to people newly involved in fMRI research. So that is a common misunderstanding of the fMRI research. That first important thing is we need to think in cognitive processes. We can talk about something about the cognitive process from the brain data. So if people do not accept in this philosophy, we cannot really do any fMRI experiment. And some people want to use fMRI as some better alternative of their approach or the familiar approach. But that is, I don't think it's a good idea, because the fact fMRI measure is quite different from other measures like reaction time or paper self-rating. So yeah, we should think very differently. So we should regard fMRI as different measure. That's the one thing. And also, many people are very used to think about, familiar with thinking on the framework of language, but cortical process is not only, of course, not only language, and language-related process is not specific, often not specific to language. So people need to be aware that they have to get out of language framework. Also, the people need to be naive about their ideas, because we will talk very different questions using very different measures. So, so particularly for the experts, they need to be consciously naive. That is one tip. And the other one is, you need to think with collaborators. And fMRI includes many different aspects, different technology, and needs very different knowledge that no one knows everything related to the study. So don't hesitate to ask collaborators. And fMRI, so therefore fMRI is a team project. So it's notoriously a team project. There are so many co-authors in the paper. So you may understand why it is. And some people say, I will start the fMRI after I learned basic things about cognitive neuroscience. But I don't think it's possible, actually. There are so many knowledge. And I think we can start from just saying some region related to this cognitive process. If you have some hypothesis about cognitive process, we can discuss without knowledge about which region it would be. We can learn it after design is completed, or actually even after the data is obtained. So we need cognitive hypothesis about cognitive process, but we don't need specific hypothesis about neural structure. And finally, very practically, many people worry about money, but first you should worry about manpower. Actually, the fMRI is really manpower consuming. So I always ask, do you have time to perform experiment, to program the task and scan and analyze and actually write the paper. And many active researchers do not have sufficient time. So most important thing that who want to get into this field have to think seriously is who do this experiment and analyze the data and write a paper. And some people try to ask his or her student to do that, but analysis requires enthusiasm. Serious enthusiasm. So the only first author can analyze the data and write a paper. So such manpower issue is the most critical issue. Of course, we need some money to do some experiments. But yeah, actually, I think money is everywhere. If you are ready, I mean, if you have a really good experimental design, you can apply it to some grant and they will give you money, I'm sure. So yeah, the most important thing is manpower. Yeah, that's it. Thank you for your attention.